Hello, everyone. Welcome to webinar series. Today, the topic is the PM2.5 emission monitoring sampling in stack. The speaker today is Mick Sauber from Apex Instrument. He is the international sales manager to respond for all country for the stack emission sampling instrument. Okay, I will pass to Mick to continue the webinar.
Okay. Thank you, Sam.
Okay.
Good morning, everybody, or good evening from where I am here on the east coast of the United States. As Sam said, I'm Mick Zulpo with Apex Instruments. And for those of you who don't know Apex, we are one of the world's leading manufacturers of isokinetic sampling equipment. And we have customers, both private industry and governments in, I would estimate, about 130 countries around the world. We have been in this business for 35 years. And not only do we pride ourselves on bringing good quality isokinetic equipment, but we also enjoy helping to educate and assist technically our customers with the methods used for sampling isokinetically. I may have met some of you last year, during my visit to, time goes very quickly, to Bangkok. If I have, nice to see you again, and if not, it's nice meeting everybody for the first time. So let's jump into our presentation here. Sam, you can see that, right? You can see the presentation?
Okay, good.
Good. Okay, perfect. So this morning, we're going to talk specifically about US EPA Method 201A, which has been designed and is specific for sampling of PM2.5 and PM10, or PM2.5 individually or PM10 individually. And we'll talk about how each three of those parameters can be sampled individually or all together. So this morning we'll quickly discuss about quantifying what is the PM that we're looking for, the particular sizes that we are looking for in these small dust concentrations. We will take a look at US EPA Method 201A itself and the parameters around the method. And then, having a little understanding of the method, we will review the equipment used for Method 201A, specifically the Cyclone, which is unique to this method. We'll talk about the 201A method as a complete system, and then we'll briefly discuss the limitations of Method 201A. I think it's important to understand that there are some challenging stack or chimney conditions that would not be conducive or very good to performing this method, and other considerations may need to be taken into account. So I'm assuming most people joining us today have either very, very good or at least a basic understanding of isokinetic sampling and what that entails with regards to the basics of Method 5, which is sampling for total suspended particulate captured on a single filter, weighed in a laboratory to get a total capture amount, which is then divided into the amount of gas that has been sampled through the system to help us determine our emission rate, or how much dust is being emitted into the atmosphere from that particular source. So knowing the basics of isokinetic sampling, most or all of the US EPA methods are then variations of that basic method 5 for sampling total particulate. And method 201A is no different. So the US EPA developed this method to describe the procedures that you as the stack tester would follow to measure filterable particulate matter, so the dust in the stack, equal to or less than a nominal aerodynamic diameter of either 10 microns, 2.5 microns, or the values of sizes in between 10 and 2.5. So this method can be used to measure the coarse particulates, which is usually everything considered PM10 or larger, and the concentration of smaller particulate, PM2.5 and smaller. As a side note, in recent times, the US EPA has been investigating the possibility of sampling PM1 with the same cyclone technology. It is not officially a method from the EPA right now. However, as research continues and medical science continues to discover that the smaller the particulate, the PM size, the deeper into the human lungs and the body those particular small pieces of dust go, and the health problems that incurs, the US EPA is constantly considering how we can measure smaller and smaller particulate size in our emissions to understand the threat to the general health. And we believe in the future that would be an extension of Method 201A, which right now only considers PM10 and PM2.5 as the two sizes of PM2 to look for. So just a quick overview to give us a look at an understanding of what we are actually sampling, what we are looking for. So PM2.5, as you can see there, is considered fine particulate. It's small particulate. It can only be seen with an electron microscope. It cannot be seen by the human eye. And most of the PM2 that we would be sampling or looking for from a stationary source would come from things like an automobile, an industrial process. But in natural occurrences, you could be thinking of things like forest fires and so forth, with the emissions coming off that, looking for PM2.5 in ambient sampling. When we talk about PM10, we consider those coarse or larger particles. As you can see there on the right, the reference to the image there, where the PM10 take up a substantially larger section of what would be considered the average human hair. When we then look at the PM2.5 size, about the same amount of particles of the PM10 that cover the human hair, PM2.5 cover the PM10 size. So they are very, very small. And you can see a reference point there to what would be considered fine beach sand that you would find on any regular beach. So even though we consider PM10 large or coarse particulate, they are still quite very, very small. And oftentimes you'll find this from a source like crushing or grinding, mill work, mines, things like that. And then obviously larger facilities in the industrial process from an emission point, from a chimney or a stack. So these are the two particular PM sizes that this method would be looking for. So prior to Method 201A, which was developed in 1990, the US EPA was using a device that would had a 5-component measurement device which would separate the particles into 6 class sizes. And we currently still have a very similar device like that right now. I don't have an image of it in this presentation, but it's called a cascade impactor, where we can actually do particle sizing of 7 particles. The complexity of that particular device is that each of the 7 stages of capture vary the size of the PM captured in each stage depending on the individual source, the flow rate, and the calculations. So the EPA themselves figured that this was very, very a difficult test to repeat and get the same or similar results every single time due to the variation of those captures. So the EPA went looking for a device that could have a constant capture size of particle in each particular stage. And hence the cyclone, the PM cyclone that we use today for Method 201 was created. And what is good about that, as I said, is you can test a source, come back in 6 months and test it again, and use the results from both of those tests to make comparable results. So now you can see if there's improvements or no improvements in that particular source by comparing the results of these tests. So there, as you can see there in the second point, as I mentioned, the component used by the existing or current Method 201A provides for 2 size classes, those larger than PM10 or those equal to or smaller than PM10 in diameter. Method 2, that is if you were using only a PM10 head, which I'll show you in a little bit. Method 201A also adds the parameters to use basically 2 cyclones in series. So you can first do a PM10 capture, particulate larger than PM10. In the second stage, you can capture everything between 10 and 2.5 microns. And then finally, in the last stage, you can capture everything smaller than PM 2.5. So in effect, you're actually doing maybe 3 tests in one, which can be very valuable data to maybe the reporting government or your customer for whom you're doing the test as well. So some key ideas, key notes about the actual method itself. The selection of the nozzle, which in this kit you would actually be supplied 12 nozzle sizes, unlike the typical Method 5 isokinetic kit, which would come with about 7 nozzles. You'll actually have the choice of 12 here. And nozzles size is based on a calculation that you do with certain parameters like flow and moisture and so forth, and based upon your delta P minimum and maximum range. So really the focus of selecting the nozzle is based on your flow rate, and obviously every source is different. So you would first have to investigate the flow rate of this particular stack that you would be testing to help determine the calculation to select the correct nozzle size. Also, another point is if you're interested in the small particles, isokinetic sampling, just like Method 5, is required. However, it's not as important as it is in Method 5. Method 5 states that your isokinetic range must be plus or minus 10% of 100% isokinetic to be considered a valid test. Method 201A broadens that, makes that isokinetic range larger by saying a valid test only has to be within plus or minus 20% of 100% isokinetics. So they give you, they double the range that you can sample outside of isokinetic range. Now, as a point to that as well, sampling point times are not necessarily considered isokinetic, but they are considered proportional to the stack velocity. So ideally, if you're sampling at 70% of the stack velocity, if the stack was to increase flow or decrease flow while you are doing this method, you would follow that trend of either increasing your sample rate, flow in, or decreasing it to match the changing flow of the stack, but you're not necessarily sampling isokinetically. You're sampling always at that 70 or 80 or 90% of the actual flow of the stack. So that's the difference when you consider isokinetic sampling versus proportional sampling. And there are other methods that do proportional sampling. And the easiest one that comes to mind is method 30B, doing the sorbent trap method for mercury sampling, vapor phase mercury sampling out of a stack. It also samples at a proportional rate, not an isokinetic rate. Further notes on 201A is basically the sample train is exactly the same as doing a basic method 5 test. You have a probe, you have 4 impingers, you have your console, your metering box with your gas meter and your orifice. Everything else is exactly the same except for at the front of your probe, you are now adding the cyclone to the front of the system, and that will act as your capture point, your filter, rather than having the filter in the hot box at the back of the probe. But everything else in the system will remain exactly the same, as you're probably familiar with. It requires, just like method 5, a pre-leak test and a post-leak test to make sure that there are no ambient air being brought into the system while you're sampling. And just as a point that that sampling or the cyclone must be removed to do both of these leaks and then put on back after the fact. So you're really you're not leak checking the cyclone itself, but you're leak checking the rest of the system. And then, as I've stated before, it offers users the PM2.5 and PM10 cyclones together in sequence, in tandem, and I'll show you a picture of that here shortly. So most of our customers around the world and what's typically done here in the US is a combination of PM10 and 2.5 together, because it allows you to use the same amount of time to collect basically 3 times the data that you would otherwise. So just to review very, very quickly, to make sure everybody is familiar here with an isokinetic system based on that method 5 that we discussed. We can see here at the front, this would be our method 201A PM cyclone here, and we'll go into further investigation of this particular cyclone a little bit later in the presentation, because this is what we want to focus on today. Your filter here is actually part of the cyclone construction, which I'll show you again later. Then you have your probe like you would your method 5. You would come to your first impinger. Theoretically, this box will not be here. That would be used for your method 5. So you're going to bypass that. You're going to go straight into your first impinger. You would have a very similar impinger set up to your basic method 5, with the first impinger being empty. your second impenger having distilled water, 100 ml of distilled water, your third impenger being empty, and highly recommended by us is the last one having silica gel to do a final moisture removal and removing any acid gases that may be remaining in the sample gas in a last attempt to make sure we have a dry and clean sample gas exiting the last impenger, so we are protecting our dry gas meter in the console for longevity. If this is done correctly, I've seen isokinetic sample boxes last over 20 years in the field. This is important to keep the equipment operational, functional, and working accurately. A point while I'm talking about this, just a little stack tester tip from years and years of experience. Many of our clients and myself, we put a small amount of cotton wool right here in the last impenger outlet, right here, right in the glassware. And all that does is act as a plug, a safety net, that if for some reason you were to have a sudden surge of vacuum come through the system, maybe you have a blockage at the nozzle and all of a sudden it removes, it falls away, and you have a lot of extra vacuum suction coming through the system. This will actually prevent the silica gel from coming up the arm, down the sampling line, and into your console. So it acts as a safety device, safety mechanism to have just a small amount of glass wool put in this last impenger exit arm. I highly recommend doing that for all methods. It could save a lot of effort and a lot of heartache getting silica gel into your gas meter, which gas meters do not like silica gel. So just a little stack testing tip. A little bit more on Method 201A. The pitot tube coefficient will be different than the one you typically use for your Method 5 testing. And that's due to the pitot being adjusted, being moved kind of to the left a little bit to make room for the sampling head. The sampling head on this cyclone is quite large. It's round. It's about 3 inches or 10 or 12 centimeters in diameter. So we need to have the pitot come around to the side of that. And because of that, the pitot coefficient will change. So just as a point that the EPA for Method 5s allows a default pitot coefficient to be used for all pitots, Method 201A specifically says that the pitot to be used for Method 201A must determine its coefficient via wind tunnel calibration. So you must calibrate the pitot with a wind tunnel with the sampling head attached, the PM cyclone attached, to determine your coefficient. You cannot use the standard default coefficient that is stated in Method 5. So just as a point, you must have a wind tunnel calibration done to meet the method correctly. The probe blockage factor must also be accounted for due to the size of the PM cycling head. We'll actually touch base on this later on in the presentation. I'll talk about the size of the stack and the maximum and minimum sizes that you must have to allow for the blockage, because you're putting so much material into the stack. If you overload, if you block too much of that flow, it's going to bias or change your results drastically. So we can talk about that further later on. And then during your port changes, you, unlike method 5, you would maintain your flow, your suction, until the sampling head is completely removed from the port. So basically you are continuing to capture that gas, that PM, all the way until the cyclone comes into the ambient or outside air. This is different from method 5, where once you've finished sampling your last point, you would actually turn off your suction, remove the probe from the stack, put it into the stack to your first point on the other side, then begin sampling again. You would actually slightly verify that by allowing the sample to continue, the vacuum to continue all the way until the PM is in the ambient air. Then you would turn off your sample, and then you would resume sampling just before you put the cyclone back into the stack, and again start your sampling instantly when you insert the probe into the stack. So again, a small variation to the basics of doing total particulate for method 5. When you have done all of your testing over the stack and you pull out the probe from the stack, you stop your pump. Once it's clear, level, and stable, stop the pump and record all your values. So you're actually going to stop your pump after you've pulled out the probe and all of the values become constant once again from moving the stack, from moving the probe. It's important to stay isokinetic or proportional since we're sampling PM. When we're using cyclones, we must use the flow rate designed for the cyclone to maintain the proper cut size. We want to make sure we're sampling within our estimated flow range to make sure that when we have selected the nozzle we want to use, it is making sure that the cyclones are operating correctly and separating the PM sizes correctly. In not doing this, if not performing this correctly, you will get different PM sizes in different parts of the cyclone, and then you won't be having a valid test. You'll be having the data skewed, not being correct in terms of what size PM you're actually capturing. So let's take a quick look here. This is our Method 201A Cyclone. So this was the device we saw at the front of our traditional isokinetic sampling system. This is the combination of both PM10 here and our PM2.5 cyclones. And as I mentioned before in the picture, this is our filter. It's a 47 millimeter glass fiber filter, provided the temperature is okay for glass fiber. If not, it may be Teflon, but it's a 47 millimeter size filter here at the back to do that final capture of the particulate in this method. So this is the nozzle that I referenced before in terms of collecting 12 of those come in the set, and must be determined the correct size nozzle to be used prior to sampling, just like you would with your method 5 sampling. The sample will come in the nozzle, the PM will be filtered here, continue down, filtered here, and finally in the last filter. And in a couple of slides, I actually have a very good cross-reference of this to show exactly where the PM sizes are captured in this particular design. Just to make reference for everybody that if you're doing the combination of PM 10 and 2.5 together, you must allow yourself a 4-inch port opening on the stack. 4 inches, yes. Typically is enough for this particular one.
Okay.
We have one other design that needs 6 inches, but this one would be 4 inches. And I mentioned that because for method 5, you really only need a 2-inch opening. But because of this size, we do need 4. And I know for many stack testers, locations can be challenging at best on the platforms and access to ports and things. So if you are going to the field, maybe to a new site, it might be great to ask your customer either to provide for you a 4-inch port or ask them if they already have a 4-inch port to make sure you can do your PM2.5 testing when you arrive. I'd hate to get to site and realize they only have a 2-inch port and you cannot. So this is again a cross-section of all the individual parts that go into our 201A Cyclone. We have in basics our 12 individual nozzles here that we would select after our calculations. We have our PM10 Cyclone here. This is a nozzle, and if you're looking closely, you would actually see that this design here is basically the same button hook or curved design as a regular isokinetic method 5 nozzle, just reversed. So it's almost like we have an isokinetic method 5 nozzle as part of this design, leading to our PM 2.5 Cyclone. And finally, our last capture here on our 47 millimeter filter at the back after both of our cyclones right here in our system. This metal piece here is just our bracket. It's just a support piece of metal to support the weight of this particular design while it's sitting in the stack. It's just functional for support. It adds no sampling functionality to the system. Again, this is kind of an exploded view of all the individual parts and how it all goes together, because obviously we need to be able to unscrew all of these parts to get our particulate capture and get it removed for laboratory analysis, for weighing, to see how much we've actually captured. So you would need to get familiar with undoing and putting back together this complete system as you recover the sample every time that we do this sampling in the field. Again, just to show you all the individual parts that go into what we're talking about, it is quite a complex design, the Cyclone, but as I mentioned at the beginning of the presentation, it's very, very accurate. Provided that you follow the method correctly, you would be able to do repeatable tests and have repeatable results every time that you use this equipment, which allows you then to use this data for determining improvements and so forth in emissions of a particular source. So this is the slide I was talking about earlier. It shows a great cross-section of exactly where each of the 3 PM sizes are captured in this particular cyclone. So you can see at the front here in the yellow, this would be everything larger than your PM10 dust is captured in that particular section. And you'll notice there as well that the nozzle is also highlighted in yellow. It's important, just like it is in your method 5 test, that you recover all of the dust that's been captured in the system, including the dust that is inside of the nozzle. The next section, as you can see here, which is basically our reverse isokinetic button hook nozzle design here, and our PM2.5 cyclone, captures everything between PM10 and 2.5. So you'll capture all sizes between those two PM ranges. And then finally, the small amount of tubing leading to the filter. And this here is our actual 47 millimeter filter inside of this particular housing. That and including this tubing leading to it would capture all of our PM2.5 smaller particles behind this. Now you can see there, there's a note right at the back of this that says condensable PM2.5. We do have a method here in the US called Method 202, which actually is a method with a filter at the back in between impinger number 2 and impinger number 3. And what that is actually doing, it's capturing what is considered by the EPA as condensable PM. And what condensable PM is it is particulate when in its hot, maybe wet phase inside the stack, acts and looks like a liquid. It looks like moisture in the stack. But once that particular particulate enters into ambient air, it actually turns into a solid. It turns into dust, and it creates PM dust, just like the PM dust that we can see inside the stack. So EPA also has a method to consider that you may be missing some of the particulate that actually does come from this source, because condensable particulate will pass all the way through this particular system. It will not be captured by any of this. Mm-hmm. So when you actually do a method 202, you do it in combination with a front section particulate method, whether it be method 5, maybe method 17 with an in-stack filter, or even method 201A. You would do that in combination with method 202. And then theoretically, by doing both of those, you could have an absolutely true number of the particulate exiting that stack and either staying in a dust form, in which it already is, or condensing into dust after it hits the ambient air. So this is very important. It's at the forefront of what the EPA is looking at. So I would assume that Thailand and the Thai government will be, if not already, looking at this particular information and thinking that they may also want to be studying condensable particulate in the future. So keep that in mind. It might be something you guys start to ask for soon. Just as a note, we have to have the pitot in line with our nozzle, just like we would with our method 5 nozzle, which would theoretically be back here, because it connects directly from the end of the probe into one single nozzle. So fortunately, we've designed all of our Apex equipment that you can actually switch the pitot tips here, and you can remove your PM5 and replace it with an extended particular pitot for your 201 sampling. The rest of the equipment you could utilize from your existing method 5 setup. So it makes the system very versatile. But please keep in mind, if you're looking to require a PM cyclone now or in the future for your customers to do the sampling, that we supply you the correct pitot to accompany your cyclone, so you can meet the method to the exact standards. And keep in mind that if you do combination of PM10 and 2.5 together, that pitot length will be different than if you do only PM10 cyclone, because the PM10 cyclone will obviously only be this section of that whole system. So it would actually be back here somewhere. So we have various pitot lengths that accompany each of the different options that you have for method 201A to exactly match the length of the cyclone. So your nozzle and your probe are in alignment as required by the method. This is a quick look at what I was just talking about in terms of an individual cyclone, the PM2.5 or the PM10 cyclone done separately, not together. So it's basically the exact same design. We've just removed the button hook nozzle, the little leeway that connects both of those cyclones in series, and we go directly from either the PM10 or 2.5 cyclone here to our filter. So when you do the PM sizes as individuals, you're still going to make two captures. You're going to make everything larger than PM10, and then you're going to have everything PM10 and smaller here. So you'll actually still have two instead of three captures. So keep that in mind. That's what you would be reporting to your customer or to the government. We need to also take into account high temperature applications. On the previous design, which was right here, this here is a thread. There's threads here like you would see on a glass bottle or a jar or what have you. When those threads get exposed to very high temperatures, they can melt together. The threads can become what we say in English, gold. Mm-hmm. And it's almost impossible to then remove them and separate those two pieces of stainless steel. So for high temperature applications, we actually have a design that uses this particular bolt together design. So you can see both of those designs here. They look almost identical to each other, except instead of in here where we have the threads, so we can put these two pieces together, these two pieces of steel here are smooth. They just slide in together. And then to hold the whole cyclone together, we use this particular bracket system here. And you tighten down these bolts and it pulls the whole system in tight together. Now, the advantage of this is that if the stack is very hot, you may get these bolts here to gall, and you may not be able to remove these bolts, but you will be able to cut these particular bolts right here to get to your sample. It is much less expensive to replace this 4 of these bolts than it is to replace this entire cyclone. You could go to any hardware shop in Bangkok and find more bolts that you could use for this for very, very cheap. But as much as I would like to continue to sell you PM cyclone every time it gets exposed to a hot gas temperature, it's not practical. We want to make sure that you guys can use this equipment over and over again. So we have both of these designs. Keep in mind also that we make all of this equipment in both stainless steel, and we also have an Inconel option for very, very high gas temperatures. So not only do we have the non-threaded, but we have an Inconel design here as well. So even the cyclone itself can take even increased high temperatures for your sampling needs, because we know that many stacks are quite challenging when it comes to moisture, temperature, acid gases, things like that. So this is important. Here's an image of an individual PM10 cyclone with that same non-threaded bolt design for the high temperature applications. So we can also do that for the individual PM sizes if that was something that you were in need of for your customer. Finally here, I just want to touch about thoughts on restrictions for Method 201A. As much as we would love to be able to do this method on any stack anywhere in the world, if a customer would like us to do it, we do have to consider the limitations of the method due to certain parameters of the stack, of the gas, for moisture, etc. So the first and most important point here is that filterable PM, whether it be Method 5 or this Method 201A, you still cannot really do this method in stacks with what is called entrained water droplets. So if you were to look into a stack and it looks like it's raining inside, there is actually droplets of liquid, of water, of whatever, falling down the stack. That is a good sign that this method is not applicable and we cannot use it, because those water droplets will change the way that this method is sampling the particular PM in that stack. You would also have the same constraints for a basic Method 5 test. For these stacks, what the EPA recommends is you do what is considered a worst case PM10 or 2.5 measurement by measuring the total filterable capture by some other method. And then you need to assume that the total catch is either PM2.5 or PM10 in conjunction with your condensable particulate that we mentioned for the additional method 202, which is your condensable particulate captured on a filter between impingers number 2 and impinger number 3. That's not always ideal. That's really just a guess. It's a scientific guess is the best way to put that. It's not the same as a 201A test, but maybe it's the best we can do in some situations. Other things to consider is the stack diameter. What I mentioned before is that the method specifically states that because of the size of the PM cyclone head, it cannot block more than 6% of the stack area, the diameter of the stack. You cannot block the flow of more than 6% of that particular area. So just as a reference, so you know what that 6% mark is, if you were to do the combined PM10 and 2.5 head, the two cyclones together, you're limited to doing of a stack of 26 inches or 66 centimeters and larger. If your stack is smaller than 66 centimeters in diameter, technically you will not be meeting the method. So please keep that in mind. Now again, sometimes we have no choice. The stack size is the stack size and we must proceed. So what happens here in the US is typically our customers will get local EPA approval to do what would be considered a variance, a change in the method. So the EPA will recognize and agree that, yes, we are not doing the method exactly as the EPA says, but we're doing the method as close as we can, and we will accept those results based on the best we can do. And that is also notified in the report, and then sampling can begin or continue. And then just as a point of reference as well, if you had just the single PM2.5 or the single PM10 head, 6% of the stack area blockage would confine you to sampling stacks larger than 48 centimeters in diameter. So if you do have a stack that is 48 centimeters or between 48 and 66 centimeters, and your customer wants to do all three particulate sizes, then it would be suggested that you do PM2.5 as an individual cyclone, then do a second test as PM10 as an individual cyclone. Then you would have the same results as you would if you were doing them in combination, but technically you would be meeting the method by not having more than 6% of the stack area blocked by your PM cyclone. So it's very important to understand these restrictions, because again, us as a manufacturer and you guys as a stack tester, we always want to provide our clients, our customers, the best results possible we can. And we need to understand that as skilled as we are and the hard work that we do, there are sometimes parameters in locations that are unavoidable or out of our control that would change our results and not allow us to supply our customers accurate information or accurate data. So these are kind of the main points that you would then consider for Method 201A in terms of that. So I know we're getting on to our hour, and I know everybody's eager to start their day down there in Bangkok or Thailand, wherever you are, and get working for the day. So I'd like to thank everybody for listening. I hope we've been able to give you a brief overview of Method 201A. I promise you it's going to become more and more important. I know last time when I was in Bangkok, people were telling me how important the ambient sampling of PM2.5 has become in Bangkok, and that information is being shared with the general public in live data through, I think it's an app on the phone or something you can download to see the air quality in the city. And obviously source emissions for that particular PM2.5 or PM10 is also a very important consideration. So it's just important as sampling the ambient air. So there'll be a lot more of this work coming in the future. So we're here to support you. We're glad to work with Neediss and answer any technical questions that you have on this method or any of the isokinetic methods as you continue to hopefully discover new methods and offer your clients more and more services that are important to us all. So thanks again, and I'll be happy to answer any questions if anybody has any at this time.